Hello, everyone. I'm Michael Carlos Kleiss, Professor of Architecture at Kleiss University.
I'm SIDA DAI, a PhD student working with Dr. Carlos.
And what we're going to present today is a method that introduces computer-generated design into origami design through shape grammars.
In previous origami design method, rigorous and complicated mathematical calculations takes a lot of time and energy from the designer and demand knowledge that they might sometimes lack.
Our research is looking to simplify the design process of a crease pattern by generating and applying shape grammars and shape rules. As a blank space in the current design field, generative design of shape grammars origami base greatly expands the possibility of origami design and the use of shape grammars in computers for origami.
There are also some important research or computational design methods for origami we want to mention. For example, the Tree Maker by Robert Lang, Origamizer by Eric Demain and Tomohiro Tachi, Orirever by Jimitani, and Test by Alex Batman.
What we found is that sometimes this research is not really combined with shape grammars, which is what I intend to do in Present Right Way. To start, I'd like to introduce our research some basic concepts, such as basic folds.
First, a crease pattern. A crease pattern is a diagram that consists of all the creases in the final model rendered into one flat image. For example, in this pattern, the red line represents mountain folds and the blue line represents valley folds, and the black line represents the boundary of the median. In this case, the paper.
The crease pattern acts as the most important bridge in the transformation from a flat diagram to a three-dimensional origami structure. Since the design of the crease patterns follows a strict mathematical principles, many scientists have used computers to generate crease patterns, such as Robert Lang that we mentioned before. Crease pattern, to expand, is a drawing standard that is widely used in origami design and communication. Its an abstraction and legibility make it necessary in the process of computational design. However, unlike folding origami artwork just by hand, which emphasizes the inspiration and experimentation, the design of the crease pattern needs to follow strict mathematical principles and rules. For example, some of described in the Origami Theorem, such as Maekawa-Justin theorem, Kawasaki-Justin theorem, the Justin isometry theorem, and the Justin non-twist theorem. These are only but four of the main important theorems in which mathematical principles are emphasized to create crease patterns.
This research gets inspiration from computational generative design and shape grammars, transforming the action of folding into the rules of shape grammar. In this way, the computer can simulate and generate a large number of foldable crease patterns in a short period of time. In the next part, we will introduce some origami skills and finally define the shape grammar rules for origami.
Basic origami skills. Before the advent of computers, people invented many origami skills to create origami arts. The most basic origami skills include a mountain fold and a valley fold.
All origami skills are characterized in that all complex skill can be achieved by the combination of simple skill. For example, the combination of two reverse folds can form a water-bound base. And the combination of the water-bound base and four reverse folds can then form an open sink fold. All the above skills are composed of the most basic mountain and valley folds.
People have different standards for the definition of simple compound folds. Folds.net, for example, define simple folds as inside, outside, reverse fold, and prayer. However, in wikibooks.org defines simple folds such as inside, outside, reverse fold.
For the purpose of our research, we classify mountain and valley fold as basic folds, and we also have three folds in our definition for simple folds, which is inside reverse fold, outside reverse fold, and rabbit ear fold.
The characteristics of origami allows us to achieve complex origami forms by combining simple origami skills. For example, the water bomb can be composed of 2 inside reverse folds.
We can also continue to develop based on the water bomb base. For example, applying inside reverse fold on each molten crystalline of the water bomb base, we can get the open sink fold, a typical high intermediate origami skill. The flexibility of origami skills is the foundation of applying shape grammars in origami.
Now that we have explained a little bit on origami basic skills and how they're used to combine and create more complex origami, let's take a look at how we approach this systematically using shape grammars. We start the initial state of origami, or the shape grammar could be an unfolded piece of paper or just a simple origami base. What they have in common is that when we started using the shape grammar, the crease pattern was foldable.
So in the first row, we create a new crease line on a blank space. The crease line could be molten fold or valley fold. We use a simplified diagram to represent these two rows, which is on the right side. The situation of vertex is inside the dash circle. The first row is creating a molten fold, and we mark this as 1, 1, and a valley fold as 1, 2.
The second rule adds a new crease to an existing crease line. So it has 4 different combinations. For the angles between the creases, they meet the following requirements. If alpha 1 plus alpha 2 equals alpha 3 equals 180. This rule can create an unfoldable vertex. So we need to use intermediate rules to create a foldable vertex. Here we have additional starting rules. Rule 3, where alpha 1 and alpha 4 and alpha 2 equals alpha 3. Also, alpha 1 plus alpha 2 equals alpha 3 plus alpha 4, which equals 180.
And in rule 4, alpha 1 equals to alpha 3 plus alpha 4. And in rule 5, alpha 1 equals to alpha 6, alpha 3 equals to alpha 4, and also alpha 1 plus alpha 2 plus alpha 3 equals to alpha 4 plus alpha 5 plus alpha 6, and they both equal to 180 degrees.
In the process of using this shape grammar, not all right-hand side designs create a foldable pattern. To solve this problem, we need to check if the vertex is foldable or not. Then we need to create a special type of rule that transforms the unfoldable vertex into a foldable vertex.
In this research, we define such shape grammar rules as transformation rule or intermediate rules. One of the series of these rules are shown here. It creates a new line connected to the vertex, and the angles between crease lines meet the requirements, which is alpha 6 equal to alpha 5, and alpha 6 plus alpha 7 equals to 180 degrees. And also, the final crease pattern needs to satisfy all the mathematical theorem to form a foldable crease pattern, because an unfoldable crease pattern is meaningless in origami design.
Take a look at the example before, in which we see a derivation of a shape grammar using our basic rules. In this example, on the final design on the right, you will take notice of vertex V5. This particular vertex is composed of 4 valley lines which will not meet the requirements of the Manikawa-Justin theorem. What is more, V5 does not exist in the shape grammar rules, so we must actually do something to correct this problem. Here we have an example of using a complete shape grammars to generate a classic crane in origami. You're looking at the derivation and the creation of different folds, mountain and valley, and a combination of using our rules. Our rules are indicated under each of the arrows to determine which is the rule that we're using. Until step number 6, what we have is created an unfoldable pattern. Then we need to apply rules to make these corrections. In step number 7, since the folding of the crane head is similar to the tail, we have to repeat the operations on the other sides of the mountain line. After that, we have completed crane origami design in which we have used successfully our shape grammar.
And the advantage of shape grammar is that it could directly manipulate the shape without the consideration of the mathematical principles behind it. This means we can hide complex mathematical principles in shape grammar rules, and user could use shape grammar-based design tools even if they don't know the shape grammar or origami principles. This will greatly reduce the threshold of origami design, allowing more designers to play with origami.
In this research, we're trying to find a balance between the manual origami design and the computer origami design. The folding action in manual origami is transformed into the shape grammar operation of creating a crease pattern. First, we extract the key folding actions through the analysis of the origami. Then, different shape grammar and shape rules are created to express the changes of the crease patterns of each vertex. Finally, according to the theorems of origami, further improve the syntax and determination rules of the origami shape grammar. The diagram that you see right here shows a typical process of using the shape grammar in origami. We start from the starting rule in the paper or existing basic pattern. After, we find a set of intermediate rules that will create additional folds. We need to check if the termination situation, if the answer is yes, we need to go back to a former foldable situation and the termination rule is unfoldable. We will ask the user if this is the pattern that you want, and if the answer is yes, we get our first result. If the answer is no, we need to go back to the start rule and start with other steps again.
We also have some more examples. We use the shape grammar to design a series of origami units in a generative design way. These units can be further applied to the adaptive facade in architecture.
What you're looking at here is a crease pattern that is being generated by the shape rules and that is being simulated into origami by Origami Simulator.
And by providing architects with easy-to-use design tools and methods, this research will greatly promote the application of origami in the field of architecture and design. We can also create a large number of origami forms with the help of computers, which could greatly expand the design of origami patterns.
As we discussed before, some of the crease patterns that we created using the shape grammars had problems folding into actual origamis. Further refinement of the actual shape grammar will be necessary in order to produce only designs that can successfully fold. We found that the shape grammars produces an abstract design, in this case, the crease pattern. Then when it's transformed into an actual design, the origami, through the actions of folding. We believe this exercise can be used in the teaching and application of shape grammars and design, as well as origami into design. Thank you for your attention, and if you have any questions.